right? So let's understand how a diode can be used as a voltage rectifier. Now, basically, what is rectification? Okay, see, in a generator, okay, or uh, what do you call hydroelectric power generators, fine. The voltage that is generated or the EMF that is generated is an alternating EMF. What is an alternating EMF? It keeps changing its polarity. Okay. For some time it is positive, then sometime it will be negative. So basic AC voltage, like you know the equation E is equal to E naught sine omega t plus phi. Okay. So it varies sinusoidally like this. For some time it is positive and sometime it is negative, and so on. Okay. Now for many devices, this kind of voltage is not uh, what do you say? This kind of voltage is not required. Many devices require a voltage which has the same polarity always. Okay. So basically what we need to do is prevent the voltage from changing its polarity. Okay. So that is what we call as rectification. You have to convert an AC voltage, okay, which is what we call as an AC signal, okay, into a voltage which is either always positive or always negative. It should not keep changing its polarity. Okay. Now there are two types of rectification that you can do. In one kind of rectification, what we do is we remove one half cycle. Okay, we remove it altogether. So basically what happens, suppose you remove the negative half cycle, then the output you see will be like this. Right? It's a varying potential, it's a varying voltage, but it doesn't reverse its polarity. Right? This kind of rectification is called half wave rectification. There is another kind of rectification also. In the other kind, what happens? The negative half cycle is also converted to positive, and that is called full wave rectification. See, whatever negative part would have existed here, it gets converted to positive. Okay, this is also still a varying EMF, but it's always, I mean, it always has the same polarity. This is called full wave rectification. Right? Many devices are not designed to work directly with alternating current. Okay, they need voltage only with single polarity. Okay, or voltage with the same polarity always. In such devices, you will have to first rectify the voltage, okay, before it is supplied to the device. Now, let's see how this can be done. First, half wave rectifier. Suppose there is an AC source. Okay. When you connect it to a load, load is always indicated by a resistance. So load is basically some device which makes use of this voltage. Okay. Let's say the resistance of the load is RL. Now, whatever is the input you give, V is equal to V naught sine omega t, okay, or you may include a phase constant also if you want. The same voltage appears across the load. Okay. Now, this is an alternating input that we are supplying. So for some time, this side will be positive, this side will be negative, and in the other half cycle, this side will be negative and this side will be positive. And you will see the same across the load as well. Okay. So for some time, current will flow in the clockwise direction or it will flow in the downward direction through the load resistance. And for some time, in the other half cycle, it will flow in the upward direction. So if you take voltage across this resistance now, okay, you call it as the output voltage. What we supply here is the input voltage, and the voltage we see across the load is called the output voltage. Now, when you apply the input voltage directly, or when you connect the input AC source directly across this load resistance, for some time this side will be positive, this will be negative, and for some time this will be negative and this will be positive. The output voltage will also be an alternating voltage only. Now, what we want to do is we want to cut off one half of the cycle. Okay. So what you can simply do is connect a diode here. Assume the diode is ideal. Now what happens? See, diode is basically a device which allows current only in one direction, and it will allow current only when it is forward biased. Okay. Now you know the triangle side is the P side, the line is the N side. So for this diode to be forward biased, the P side should be at higher potential than the N side. That happens during one half cycle of the uh, input voltage. Fine. So consider the input like this. Then whenever this side is at higher potential than this side, you will see current flowing through the diode. Okay. And current flows in this direction. So through the resistor, it flows in this direction, means through the load, it will flow in this direction. And through a resistor, current flows from high potential to low potential. So this side will be high, this side will be low. You will get an output voltage, right? And whatever is the input, you will get the same output. But when the negative half cycle is going on with the input voltage, what happens is the upper end will be at lower potential, lower end will be at higher potential. Now the diode is reverse biased. P side is at lower potential, N side is connected to the higher potential of the battery. I mean, higher potential terminal of the battery or source. Then the diode will not allow current to pass through it. If there's no current through the diode, there's no current through the load resistance. If there's no current through the load resistance, then the output voltage will be 0. Okay. So that is how. Now if you see the output voltage or the variation in the output voltage, only during one half cycle of the input, you will see output, which is same as the input. During the other half cycle, there will not be any output at all. So simply by connecting a diode beside the load resistance, you can perform half wave rectification. Now, when this kind of a voltage, okay, this output voltage passes through the load resistance, obviously, see, there is voltage for some time and then there is zero voltage for some time. Again, you see a voltage and zero voltage, a voltage and followed by a zero voltage. Now, only when there is non-zero voltage across the load resistance, you can expect some energy conversion to happen. Okay, so suppose it's just a bulb or something. Of course, bulb does not require a rectified voltage. Bulb can work on AC voltage, whatever be the device. Okay, only when the voltage is supplied, it can perform its function, right? So basically, in this kind of rectification, in half wave rectification, the problem is that you are not always supplying energy to the device. Okay, you'll only be supplying energy for half of the time. Okay, the other half of the time you are supplying zero voltage, so that device will not work, obviously. Fine. The next kind of rectification is full wave rectification, in which the negative half cycle is also converted to positive half cycle. Okay, for this we use a simple circuit. Let me copy the circuit diagram. Right. Now let's first consider a transformer. We know what a transformer does. It can, there are two types of transformers, step up and step down. If N2 is greater than N1, it's a step up transformer. If N2 is less than N1, it's a step down transformer. This is the circuit symbol for a transformer. Consider a step up transformer. Now, transformer works on the principle of mutual inductance, right? Or electromagnetic induction, you can say. Suppose on one side you connect the input voltage. And we also know that transformers can do that step up, step down function only with alternating voltages. They don't work with direct voltages because you can't expect induced current with induced what do you call like to induce EMF, you need a time varying magnetic field. A time varying magnetic field can be produced by a time varying current, which can be produced by an alternating voltage, not by a direct voltage. So suppose this is the input voltage. So basically what happens, the input voltage creates a variable current in the first coil. That first coil creates a magnetic field, which will pass through the second coil. And the magnetic field through the second coil, which is varying, time varying, will induce an EMF in the second coil. And that is what we call as output voltage. So output is taken between these 2 points. Now you consider the second coil of the transformer, secondary coil. Imagine some magnetic field lines passing through it. Let's say the field strength is B and the cross-sectional area of the coil, okay, is A. Then the flux through each turn of the secondary coil is BA. Whatever is the magnetic field passing through each turn multiplied with the area. That will be the flux through each turn. Then the total flux through the secondary coil will be number of turns in the secondary coil N2 multiplied with BA. Okay. And then from Faraday's law, EMF induced in the secondary coil will be d phi by dt, derivative of this. So N2A dB by dt. Magnetic field will be a time varying magnetic field. That is how you get EMF in the secondary coil. Okay. So the EMF that you get across the secondary coil depends on the number of turns. Fine. Now, if you collect the output across this point and this point, then all the turns are included. Okay. Let me just extend this. Basically, you will be collecting the EMF induced across all the turns. Now, instead, if you connect a wire somewhere in between, okay, let's say you connect another wire here itself, you can even collect or you can even supply the voltage between these 2 points to another load. Okay. Now, between these 2 points, the 2 points that I marked in orange, there are fewer number of turns. Fine. If the number of turns is less, then the EMF will also be less. But you will get some EMF. Right? So suppose the total number of turns is N2, but the number of turns in that between those two orange points is some X. Okay. The EMF you get between those orange points will be proportional to X. So you can say that the EMF between these two is total EMF in the secondary into X divided by N2. Okay. So depending on where you connect that other wire, you can get lesser voltages also if you want. Now, that is what we do here in this device called a center tap transformer. Now you can see that the center tap transformer on the right side on the secondary coil, to the secondary coil, there are 3 connections. Okay, let's mark them in orange. 1, 2, and 3. Fine. The first one and the third one are at the ends of the coil, okay, but the second one is exactly in between. So you can say that EMF between 1 and 2 will be equal to half the EMF between 1 and 3, half the induced EMF between 1 and 3, if that wire is connected exactly in between. Okay. Now, what is the advantage of using this kind of a transformer? Let us study this circuit that is shown here. Assume an input voltage, okay, input alternating voltage is supplied here. So basically what happens, for some time, this end will be at higher potential, this end will be at lower potential. Let's call that the positive half cycle. Okay. Now, when the upper end is at higher potential, lower end is at lower potential, on the right side, let's mark 3 points, A, B, C. Okay. Now, voltage at A or potential at A will be greater than potential at B, which will be greater than potential at C. This is what happens during the positive half cycle. Now, if potential at A is greater than potential at B, okay, you look at the circuit. We are using 2 diodes now. A is directly connected to the P side of one diode. Okay. Now, among all 3 points, A is at the highest potential, and the other side of the diode, other end of the diode, to what is it connected? It is connected to C. Okay. Now you know A is at higher potential compared to B and C. So that makes this diode forward biased. Now you see the diode D2. P side of the diode D2 is connected to B and the N side is connected to A. Now you know B is at lower potential than A. So basically this time, I mean during the positive half cycle, the diode D2 is reverse biased. It won't allow current. Okay. D1 allows current to flow through it and current flows this way. D2 does not allow any current. Okay. Now the current flowing through D1, how does it pass or how does it flow? Basically, it will have to go like this. Through the diode D1, goes through the load resistance, and this way. So there is a proper path for the current to flow. Fine. So in which direction is current flowing through the load? It is flowing in the downward direction. Current flows in the downward direction means potential at X will be greater than potential at Y. So this side will be positive, this side will be negative. You will get a positive half cycle in the output voltage as well. So when a positive half cycle is going on in the input voltage, you'll get a positive half cycle in the output voltage as well. Okay. Now suppose the negative half cycle of the input voltage is going on, means the upper end is at lower potential and lower end is at higher potential. Then the same will happen with ABC also. Okay. Okay, wait, they have already used A and B here. Let me remove these just to avoid confusion. Now what will happen? Potential at A will be the least, lesser than potential at B, which is lesser than potential at C. Okay. Now A is connected to the P side of the diode D1 and C is connected to the N side. So diode D1, since A is at low potential, it means the P side is at lower potential. Diode D1 is now reverse biased. It won't allow any current to flow through it. Whereas the diode D2, if you see, B is connected, okay, wait. C is connected to the P side of the diode D2. You know C is the point which is at highest potential. So diode D2 is forward biased and it will allow current to flow through it. Okay. So this time how will the current flow? Through the diode D2. It flows to the load and in the load it will flow in the downward direction. And this way there is a proper path for the current to flow. Okay. And what is happening now? The negative half cycle of the input voltage is going on. Even now, the current through the load is in the downward direction itself. When current through the load is in the downward direction, it means the end X is at higher potential and the end Y is at lower potential. Okay. Which was the same even when the positive half cycle of the input was going on. Okay. So whether the input voltage's positive half cycle is going on or the negative half cycle is going on, you will get the same output. Okay, you will always get a positive half cycle in the output. This is what we call full wave rectification. So remember, a full wave rectifier circuit requires a transformer and two diodes. Why two diodes? To allow the flow of current, okay, or to make current flow only in one direction through the output uh, or through the load resistance. Right. Simple only. One diode for half wave rectification, two diodes for full wave rectification. You need to remember this circuit diagram. Okay. Next, we shall discuss about a special kind of diode called a Zener diode. It is denoted by this symbol, a standard diode symbol with a small variation. Okay, the inside is shaped like a Z. Right. Now, what is special about this diode? See, usually when a diode is reverse biased, okay, as long as the reverse bias voltage is less than its breakdown voltage, there will be negligible current. Okay, in an ideal diode in reverse bias, you can assume the current is zero. But once the reverse bias voltage exceeds the breakdown voltage, right, what will happen? The valence electrons in the depletion region will be pulled into the conduction band, and you will suddenly see a large amount of current, okay, through the PN junction, large amount of reverse current through the PN junction. Okay, that is what we have shown here in the IV characteristics. Once the voltage exceeds the breakdown voltage, there is a sudden increase in the reverse bias current. Now, usually regular diodes, like regular PN junction diodes, cannot withstand such high currents. Okay, cannot withstand means what? Due to the heat generated, they'll usually get burnt, damaged. But a Zener diode is made of materials which can withstand such large currents, okay, or such sudden changes in currents. I'm not saying a Zener diode is made of a material which can withstand any amount of current, but they can withstand significantly large currents compared to usual diodes. Okay. So even if the reverse bias voltage applied is more than the breakdown voltage, the diode will not get damaged. There will be a sudden increase in the reverse bias current, but the diode will not get damaged. Okay. That is what is a Zener diode. And the use of a Zener diode, or yeah, Zener diode is used in a circuit in reverse bias itself. Fine. So basically it can withstand large reverse bias currents that occur at voltages greater than the breakdown voltages. Okay. Now, how is it used in a circuit? Basically, what happens when the voltage, reverse bias voltage, fine, across the Zener diode is less than the breakdown voltage, it does not allow any current. So it behaves like an open switch. So you can think of it this way. First case, to make it reverse biased, you know, the inside has to be at higher potential compared to the P side. Fine. So if the applied voltage is less than breakdown voltage, it is in reverse bias, it allows no current, so you simply treat it as an open switch. Okay. But if the applied voltage is greater than the breakdown voltage, greater than or equal to the breakdown voltage, then what happens? Actually, see, you cannot apply a large voltage. Like the way it is used in a circuit, the Zener diode won't allow the voltage to become significantly greater than the breakdown voltage. Okay, you'll understand how. So basically, when the voltage tends to become more than breakdown voltage, what the Zener diode does is it limits that voltage to breakdown voltage. It doesn't allow it to become more than that. So you will see that the potential difference is equal to VBR itself. Okay, we'll solve one problem, you'll understand. I'll explain how it can do this. Right. So when the voltage across the Zener diode in reverse bias tends to become more than its breakdown voltage, it will become this magical device which limits the voltage to breakdown voltage. It doesn't allow it to become more than that. Okay, that is how we use it in a circuit, and it doesn't allow the voltage to exceed a certain value. So it can be used as a voltage regulator across a device. Now, what is voltage regulation? Basically, it means limiting the voltage across a certain device. Fine. Usually in AC circuits, voltage fluctuations are quite common, but the devices that we use, they are built to withstand only certain amount of voltages. If the voltage across a device suddenly exceeds to a very large value, the device could malfunction. Okay, it could undergo permanent damage as well. So it is quite common to use a voltage regulator. Fine. Usually you will see these in the adapters. Fine. The electronic devices that we use, they use adapters, the charging adapter that is there. It will have a voltage regulator inside it. So even if there is a fluctuation in the power supply, the adapter will be able to, uh, what do you say, adjust the voltage such that the device operates safely. So let's see how a Zener diode can do that. Let's consider a simple example. Suppose there is a voltage applied across a series combination of two resistors like this. Let's take some example values. Assume this first resistance is 2 ohms and this other resistance is 3 ohms. They are in series. If a voltage V is connected across this series, now you know how voltage gets distributed in a series combination of resistors. It'll get distributed in the ratio R1 is to R2. So you will see a voltage of VR1 by R1 plus R2 across this one, and VR2 by R1 plus R2 across the other resistor. Okay. Suppose this resistor R2 is a load resistor. Fine. So it's the resistance inside some device. And assume that device can only withstand voltages up to some, say, 20 volts, not more than that. Okay. So voltage across the load, or let's mark these points as X and Y. Potential difference between X and Y should be less than or equal to 20. Okay. If it exceeds 20, the device will get damaged. Fine. Now, how much voltage you actually see across the load depends on the voltage that you apply. Okay, the input voltage. Suppose this is some 40 volts. Now you have to split 40 in the ratio 2 is to 3. That is, you have to divide it into 5 parts. Each part will be 8 volts, 2 parts to the first one. That means 16 volts across this and 24 volts across this. So when the input voltage becomes 40, the voltage across the load becomes 24, which it cannot withstand. It can only withstand voltages up to 20. Okay. So basically what we need to do here is we need to connect a voltage regulator across this. We should not allow the voltage to become more than 20. Okay. So depending on the input voltage, the voltage across a particular device or a particular load could exceed its rated value. We should prevent that. So what we do is we connect a Zener diode. Now we don't want the voltage across the load to exceed 20 volts. So what we'll do, we'll connect a Zener diode whose breakdown voltage is 20 volts. And Zener diode is supposed to be used in reverse bias. They are designed for that. Okay. So suppose the breakdown voltage of this Zener diode is only 20 volts. Right. Now Zener diode behaves in different ways depending on the voltage that tends to appear across it. Now let's say the input voltage is only 10 volt. Then understand what happens. The Zener diode is reverse biased clearly because the positive terminal is connected to its N side and the negative terminal is connected to its P side. It is in reverse bias. Now in reverse bias, if the voltage is less than breakdown voltage, the Zener diode won't allow any current at all. Okay, it behaves like an open switch. If the voltage tends to become more than the breakdown voltage, then only it will allow current to pass in the reverse bias condition. So what to deal with problems in which Zener diodes are involved, you should first assume there is no diode at all. You assume there is no diode at all and check how much voltage tends to appear. Okay. Now the applied voltage is only 10 volt. You split it in the ratio 2:3. You will see 4 volt across this resistor and 6 volt across the load. Okay. If the voltage across the load is 6 volt, that means the voltage across the Zener diode, the reverse bias voltage across the Zener diode is also 6 volt only. 6 volt is not, or 6 volt is definitely less than its breakdown voltage. So what will happen? The Zener diode in this case simply behaves like an open switch. You can ignore that branch altogether, and these are the voltages that appear across the resistors. You can even tell how much current flows. Okay. Now, suppose the applied voltage is 40 volt. Just a moment. Suppose the applied voltage, the input voltage is 40. Now, if the input voltage is 40, in the absence of Zener diode, what would happen is you would see 16 volt across this resistor and 24 volt across this resistor. Now, if the voltage across R2, that's the potential difference between X and Y, becomes 24, the potential difference across the Zener diode also becomes 24. But what is the breakdown voltage of the Zener diode? 20 itself. Okay. Now see, for this potential to become 24, sufficient amount of current should pass through this resistance. But because the voltage tends to be greater than the breakdown voltage, what happens is the Zener diode starts allowing current to flow through it. Okay. And it will allow current to flow through it while limiting the voltage. Let's call these points as P and Q. Voltage between P and Q is same as voltage between X and Y. Okay. And voltage between P and Q is limited to 20 volts. Anything greater than 20, or if it tends to become more than 20, the Zener diode will allow the excess current to pass through it. It won't allow the extra current to pass through the load resistance. Okay. So it won't allow the load voltage to become 24 at all. So what does it do? Now, in the absence of Zener diode, the voltage between P and Q or the voltage between X and Y tends to become 24. So now the Zener diode will, I mean, the Zener diode will allow current in reverse bias condition because the voltage tends to become more than its breakdown voltage. So as a result, what will happen? The voltage across PQ or XY will be limited to 20. So you will see 20 volts across the load resistance. There will be 20 volts across the Zener diode as well. Okay. We applied 40 volts. The voltages you see across PQ or XY are only 20. Now PQ, XY are in parallel. Okay. So that combination has 20 volts. Then R1 will get the remaining 20 volts because the supplied voltage is 40. So voltage across R1 will also be 20. Right? I'm not saying all three will be equal, or in fact, we should have considered some other value maybe. Let's take 50 volts. If you take 50 volts, voltage across PQ and XY is 20. They are in parallel. Then the remaining 30 volts will appear across this one. Okay. So first you check what the voltage across the Zener diode tends to become in its absence. In its absence, when you apply 50 volts, splitting into the ratio 2:3, you will get 20 volts here and 30 volts here. Okay. Now Zener diode's breakdown voltage is only 20 volts, so it won't allow it to become 30. The moment it tends to exceed 20, it starts allowing current. It won't allow the voltage across or between P and Q to exceed 20. So that is limited to 20, then R1 will see a voltage of 30. Okay. Now you can calculate the currents. Current through R1. The voltage that you see now is 30 divided by its resistance is 2 is 15 ampere. Okay. Current through R2. R2's voltage is limited to 20 and that is what you see across R2. Current through R2 is 20. Its resistance is 3 ohms. So 20 by 3, 6.6 or 6.7 or 6.67, anything. That is the current through R2. Now whatever current flows through R1, it enters the junction at P and splits into two. some current flowing through R2 and remaining current flowing through the Zener diode. You can even tell how much current flows through the Zener diode. Current flowing through the Zener diode now becomes the total current minus the current that is flowing through R2. This becomes the current through the Zener, 15 minus 6.67. These are just hypothetical values that I have taken. Actually 15 ampere, 6.67 ampere. These are very large currents. But this is how a Zener diode works as a voltage regulator. Fine. So you should first see the voltages that appear across the diode in its absence. If the voltage does not tend to become greater than its breakdown voltage, you don't even have to consider the presence of the diode at all. But if the voltage across the diode tends to become greater than or equal to its breakdown voltage, you consider its presence and you consider the fact that it allows current to pass through it without allowing the voltage to exceed the breakdown voltage. Okay. And based on that, you readjust the remaining voltages and you can find out the currents as well. Let's solve another problem based on this. Okay, let's say this resistance is some 5 ohms. This resistance is 2 ohms and breakdown voltage of the Zener diode is, okay, let's take 20 volts itself. And wait, instead of 5 and 2, let's take 3 and 2. It will be easier to split the voltages. Right. Suppose we apply 40 volts. Okay. We supply 40 volts. Find out how much is the current flowing through the Zener diode. Yeah. Try this, both of you. Any answers? See, Zener diode doesn't always behave in the same manner. No, it depends on the voltage that appears across the diode. So you should first see what voltage is likely to appear in the absence of Zener diode. So assume it's not present. That's all. We applied 40 volts. There are two resistors, 3 ohm, 2 ohm connected in series. One of you quickly tell me how much voltage do you see across 3 ohms and across 2 ohms? When two resistors are connected in series or when any number of resistors are connected in series, the total voltage gets distributed in the ratio of their resistances. That's all. So it gets distributed in the ratio 3:2, means 5 parts. So 3 parts given to 3 ohm resistance, so 24 volts, and 2 parts given to 2 ohm resistance, that will be 16 volts. That is those are the potentials or the voltages that you will see across these resistors in the absence of Zener diode. So the potential difference between X and Y only tends to become 16 volts. That means the potential difference between P and Q will also be 16 volts only in the absence of Zener diode. Now, even if Zener diode is present, okay, the applied voltage is just 16 volts, which is not greater than its breakdown voltage. Okay. So the diode is reverse biased and voltage is not more than breakdown voltage. So current through the diode will be negligible. So in this case, the answer current for IZ is, sorry, the answer for IZ is 0. The voltage does not become more than breakdown voltage. Okay, so that is how you are supposed to solve problems. Now let's try this problem. The Zener diode breakdown voltage is given as 15 volts. Okay, you have to keep this in mind. Is used as a voltage regulator. Okay, is used in a voltage regulator circuit as shown. The current through the diode is how much? Okay, you can see that the diode is reverse biased. This end is positive. This is the positive terminal, and this is the negative terminal. Okay, So N side is positive, P side is negative. It is in reverse bias. Fine. Look at the resistances given to you. 500 ohms and 1 kilo ohm. Okay, that's 1000 ohms. They are in the ratio 1 is to 2. Applied voltage is 100 volt. Okay, let's do it part by part. First, let's assume the zener is not even present. Okay, if we apply 100-volt input, both of you give me answers. How much voltage will you see across the 500 ohms and how much voltage will you see across the load of 1 kilo ohm? Let's call them as V1 and V2. So when there's no zener, how much are V1 and V2? Okay, Pradyumna has given the answer. The voltages are in the ratio 1 is
66, 66 and 33.
correct, correct. Okay, so you have to split it in the ratio 1 is to 2, 33.3 and 66.6 or 66.7. Okay, these are the voltages that you see. Now, V2 is the voltage across the load, which is the potential difference between these 2 points. Let's call them as X and Y, which are also connected to the Zener diode. Fine. So the potential difference or the voltage across the Zener diode tends to become 66.7. But the Zener's breakdown voltage is only 15 volts. So it won't allow the voltage to become 66.7. See, basically what happens when all the current flows through the resistors only, then the voltage across this tends to become 66.7. But there is a zener no in between. Once the voltage tends to become more than 15 volts, it will divert the current. It won't allow that much current to pass through the load at all. So that much voltage won't even develop across the load. Okay. The zener will take some current. So now what will happen? You know that zener current will pass through the zener diode. And when current passes through the zener diode in reverse bias, you can be sure that the voltage across its terminals does not exceed the breakdown voltage. So what the zener diode does is it limits the voltage between the points X and Y. So now these voltages are useless. V2 will only be 15 volts. It won't be, the zener won't allow it to become more than that. Okay, for the voltage V2 to become more than 15, more current should pass through it. Zener won't allow that. It will start diverting current. Okay, so V2 is capped or limited at 15 volts. If V2 is 15 volts, then V1 now becomes 100 minus 15, 85 volts. Okay, now what is the use of V1? Why are we even talking about V1? Using V1, we can tell the current I. I is V1 divided by R1, 500 ohms. So 85 divided by 500 ohms. 17. Okay, 85 by 117. So 0.17 ampere is the current I. Okay. Now the current I splits into two branches. One is IZ, the current through the Zener diode, and the other is IL. So simple KCL equation, I is equal to IZ plus IL. Now the question is to find out how much current flows through the Zener diode. You can't do that directly. Okay. Only when you know the other two currents, you can tell how much is the current through the zener. Now current I we have calculated. Next you calculate the current through the load. What current is passing through the load? Voltage is 15. Resistance is 1 kilo ohm. Okay. So current in the load, IL will be 15 divided by 1000. That is 0.015 amperes. Once you know I and IL, subtract them, you'll get IZ. Okay. Is this clear? Any doubts in this? Fine. Fine. So remember, Zener diode is supposed to be used in reverse bias and it is made of materials which can withstand breakdown current. Okay, so once voltage across the Zener diode tends to exceed the breakdown voltage, it will limit it at that value. It will start diverting current and preventing the voltage from exceeding the breakdown voltage. Fine. Okay, next part is special purpose diodes like LED, photodiode, solar cell, and then logic gates. Those things we will discuss in the next class. And when will you have the next class? Saturday morning. Okay. So Saturday's class will try to finish off this chapter. Okay, thank you all. We'll continue in the next class.
Thank you.